Good morning, everybody. I hope you guys are doing well today. So I just want to start off by apologizing for having to cancel class on Tuesday. Definitely was under the weather. Still not feeling the greatest, but I didn't want to cancel, obviously, multiple classes in a row here, so bear with me here this morning. We are finally going to take a look at 5.03. I feel like this lesson's kind of been put on the back burner since last week already. We've just kind of been pushing it back and back and back. It's really not that bad of a lesson compared to 5.01 and 5.02. So hopefully you'll find success with this one relatively quickly and then can enjoy your winter break. One thing regarding that, don't forget when we return from winter break, it's a quick 2 weeks until we reach that final deadline of January 14th. January 14th means you have to have all of your work and tests in. That's not the final exam. Okay. Any questions with that final deadline or anything of the sorts? So I had also laid it out in the email that I sent Tuesday, kind of what to expect for the remainder of the semester. So today we'll take a look at 5.03. Obviously, we'd like to get that handed in before you go to break so that you don't have to do it either over break or when you return. When you come back, we do return on a Tuesday, so I'll see you guys bright and early that Tuesday morning on January 2nd. We'll take a look at 5.04. And then Thursday we'll do 5.05. The next Tuesday will be 5.06. And then the last Thursday is going to be reviewing for your final exam, or like a study day, final exam detail day. So that's kind of the plan for the last 4 classes left for semester 1, besides today, obviously. Okay, if there's no questions, we'll go ahead and jump right in with 5.03. We are learning some more identities. This time we're learning about the sum and difference identities. So right off the bat, you're going to want to add some stuff to your notes or to that poster that I had you guys or told you guys that you should probably create for your workspace with all the other identities that we've had so far. This one is the cosine of a sum or difference. So basically up until this point, we've only been able to identify what the sine, cosine, or tangent values were of specific spots on the unit circle. Now we're going to expand that a little bit more. Can I find other spots that are not identified at the on the unit circle right now, but maybe I can combine 2 values by either adding or subtracting to get a different spot on there. So for example, I don't have cosine of 15 on the unit circle right now. It's not a spot that's on that 16-point unit circle. But can we find the value still if I can use 2 spots that are on the unit circle? And obviously we can, otherwise, because we wouldn't start off with this one if we couldn't, right? But what 2 values can I either add or subtract together from the unit circle to get 15? And keep it basic. The smaller the values are, the better off you'll be. Because I know there's many combinations that probably could work here, but we want to keep it small if we can. Yeah, 45 and 30 hopefully come to mind. And we would need to use subtraction in order to get 15 there. So what we can start off by doing is saying, well, instead of cosine of 15, let's do cosine of 45 minus 30. All right, we can use the cosine of the difference identity here in order to calculate this now. So notice with this formula that you have cosine of u plus or minus v. So technically you can do a plus sign in here or you can do a minus sign in here. With our example, we're doing the minus sign. Okay. So since we're doing the minus sign, I'm going to go ahead and copy down my formula. I would do cosine of 45 times cosine of 30. And then all of a sudden we run into this symbol, the minus plus sign. What in the world does that symbol mean? All right, we'll take a look that it was plus or minus here, and now it's minus or plus here. So that means that you're basically going to do the opposite of what you had in the front. So we use subtraction here to get our 15. That means we're going to use addition in our formula. So because that symbol is flipped, you're doing the opposite of what you had out in front. Does that make sense to everybody there? So seeing that symbol flipped where it's a minus plus, it's basically telling you to do the opposite of that plus or minus that you began with. Okay. Awesome. Now the unit circle, we still need it. Let's go ahead and actually identify what the values are at these certain spots now. So let's start with cosine of 45 degrees. What is the value we get on the unit circle at cosine of 45 degrees? Square root 2 over 2, yeah. What about cosine of 30 degrees? Good, okay. Remember that the cosine values are the x values of your points, and the sine values are now the y. So what's sine of 45? 45 is nice because the x and y are the same at that spot. So we should get another square root 2 over 2, right? What is sine of 30 then? I'm guessing that's going to be my 1/2. It is. Okay, good. All right, let's combine these, or simplify it, we should say. When we are multiplying radicals together, remember we multiply what's underneath the square root sign. So 2 times 3 is 6. We do want to multiply in the denominators as well. Notice they have the same denominator. So we're going to get square root of 6 plus square root of 2 all over 4. Do not go overboard and add the 6 and 2 together. Remember, you cannot add radicals unless they have the same number underneath the square root sign. Right? You can only multiply them like that. You cannot add. So they do need to stay separated in the numerator there. This is a very common combination of numbers here with the square root signs. So you'll notice that you probably run into this quite often as an answer when you're dealing with things from the unit circle, because there's really only 3 or 4 values that you can have. Well, technically 5 if we include 0 in there. But there's not that many combinations that we can use from our points. So we're going to see a lot of this variation as an answer. All right, any questions though with how we got that answer? It's not very pretty, but the process behind it wasn't that bad either. All right, let's go ahead then and prove an identity. I know the proofs are coming back here, but they're really not as bad as we've seen in 5.01 and 5.02. Here we notice that we are taking cosine and subtracting 2 values, so we want to use that cosine of a difference identity that we just saw. So because we're subtracting here, as I use my formula, we start with cosine of the first number, which is pi over 2. And then we do cosine of the second number, which is x. And our formula says we need to do the opposite now. So we're going to do a plus. And then we'll do the sine of those values. All right. Then from here, we have to use our unit circle and simplify where possible. So we can replace cosine of pi over 2. What is cosine of pi over 2? 0, Isaiah says, and Tommy seconds that. Cosine x, we can't simplify that because we don't know what x is, so we just leave it cosine x. What is sine of pi over 2? That's our 1. Notice cosine times, or 0 times cosine x is just 0, and 1 times sine x is just sine x. So that's going to simplify just down to a sine x, and we are done. We have proved it, right? That's what we were trying to show. All right, are there any questions with that first formula with the sum or difference with your cosines? And again, you'll definitely want to have this written down somewhere because we're going to also look at sine in just a moment here on the next slide. So we'll get a formula for the sum or difference of sines, and then we'll also get one for tangent. In fact, we'll get a couple different versions for tangent. So we'll want to be able to keep these straight. And they do look very similar to each other. There's just some subtle differences between the formulas. So having that written down so we can physically see it before starting a problem is going to be really important moving forward. Okay, here is that second formula. This is for the sine of a sum or difference now. All right, so notice that in the formula, if we need to add two things together, we would use the plus sign out in front here. We use the same operation in the formula now. So in cosine, it was flipped, but in sine, it's identical. However, the difference with this formula is instead of having cosine, cosine, plus sine, sine, it's now one of each. So you're going to do sine, cosine, and then basically sine, cosine, but you'll have the numbers swapped around there. Okay, so hopefully you got that copy down here. Let's go ahead and this time instead of actually using the formula, we're going to kind of use it in reverse. It says write each of the following expressions as either the sine or cosine of an angle now. So first of all, you have to identify which formula you're using. Are you using sine or are you using cosine? So how about this first one in A? Yeah, taking a look at the formula, the first identifying piece is if you have one of each next to each other. And I do. If I have one of each, that's going to represent a sine. So we know we got to use sine. And then second thing we have to identify is do I add the numbers together or do I subtract? So that's where the operation in the middle comes into play. Because we're looking at sine, we keep that operation. So Isaiah says, yes, we want to add. I agree. So let's go ahead and add those two numbers together. What does that equal? 22 plus 13 is a 35. So essentially they were looking to find the sine of 35 in part A. All right, what about part B? Are we using sine or cosine formula there? Cosine, yep. All right, so am I adding or subtracting the pi over 3 and pi over 4? Yeah, notice with the cosine formula, you do the opposite. So we want to subtract these. All right, we do need to get a common denominator before we can subtract, though. What's the common denominator between 3 and 4? A 12, yep. So to get a 12 on each one, I'd have to multiply this first one by 4 and the second one by 3. So I'll just kind of come off to the bottom here. So when I subtract those, what am I finally going to get? Cosine of what? over 12. Yep. Good. And then last one, are we using sine or cosine formula? Cosine, but what's different about it? We are going to use cosine, but we've got to do a little bit extra work. It's flipped. It's reversed. So if I want to flip it back so it follows the formula, what is needed? So if I want to flip those two things around, what's needed? A -1. Yep, you need to multiply by a -1. So instead of just having cosine of that, let's do a -1 in front of it. We can still go ahead and combine the x and 2x inside here. Would I want to use a plus or a minus sign following that formula? It would be a plus, right? We're still going to do the opposite of what the operation was. So even when it's flipped, we still want to do the opposite of that. So technically, this is going to be a negative cosine of 3x. So just keep an eye on if they flip it around like that, because we will need to multiply by a -1 out front for that formula to work then. So they do try to be a little bit tricky like that, but we'll just make sure that we are keeping an eye out for it. All right, questions with that group of examples? All right, let's go ahead and take a look at the next set of examples here, proving reduction formulas. Basically, this is kind of the same thing that we did, I think it was example 2 we looked at. So let's just choose one of these. Which one of these would you like to try and prove? Should we do A because we already looked at a cosine one? Should we focus on the sine? I think that one would probably be a good one to look at. We already worked with the cosine one, and there's really no difference with using that identity again. So we're going to focus on the sine one since that's what we haven't really looked at yet. All right, so if we're going to use sine, how does my formula start off? So how would I start my formula off for this one? Sine of x times cosine of pi. Good. Oh, look at that. We've got Isaiah says the whole thing. Good. So sine of x, cosine of pi. And notice that if you're following exactly, you can go ahead and do cosine x, sine of pi. I also like to just kind of keep it sine cosine, but then just flip the values too. So however you like it is fine. So whether you like to do sine cosine, cosine sine, for my brain, it works. I don't know. I just got to be really like OCD with some things, and I like sine cosine, but then just flipping the values in there. Whatever works for you is fine because multiplication is commutative. You can flip around those different pieces when you're multiplying there. So it is okay to kind of rearrange that a little bit if need be. These mean the exact same thing that Isaiah's put in the chat box though. All right, let's go ahead and simplify what we can. So sine of x we can't simplify. We don't know what x is, but we can simplify cosine of pi. So what can we replace cosine of pi with? A -1. Good. Sine of pi then, we can replace that. That's probably going to be our 0, huh? It is going to be our 0. Okay. So this is basically going to give us a negative sine x plus 0. which is just our negative sine x. Good. Any questions with that? All right, we saved the best formula for last, and that's the tangent. Because tangent is a combination of sine and cosine, there's a lot of different versions that we can use here for this formula. The first one, and again, this one's the most complicated piece, leave it to tangent to throw a wrench into the system here. We can use the formula of tangent u plus or minus tangent v. Notice that if it's the same order as what you started with, you're using the same sign that which you began with, right? So this would mimic what you began with, but in the denominator, it's flipped. So you're going to do the opposite of what you had. So if you have a plus sign up here, you've got to use a minus sign down here, and then vice versa. So keep an eye on those symbols on whether it should be flipped or not. Now this is great if you are really good with your tangent, and it is useful at times. However, I do think that working with sine and cosine can be a little bit more friendly because that's what we're given on the unit circle, right? We're given those points in terms of sine and cosine. So it's easier to evaluate if you're looking at things in terms of sine and cosine. So we can go ahead and take this tangent formula and break it up as sine over cosine of the sum or difference identities here. So you can see the sine sum or difference identity happening in the numerator, and then that cosine sine or difference identity happening in the denominator there. And again, notice that it's plus minus or minus plus because sine uses the same operation, but cosine uses the opposite. So this is the one that I think will probably be used the majority of the time. However, this might be applicable if you need to simplify something and maybe you have tangent still in there somewhere. So you might find yourself using the top one once in a while, but I think the bottom one is going to be more appropriate 90% of the time. All right, so let's go ahead and prove this reduction formula for tangent. Again, I would probably use the sine over cosine formula even just to prove this reduction here. So let's go ahead and do that. Let's start with sine. And I'm just going to put x instead of theta. Just because I like to favor x over theta when I'm doing this. So just keep in mind that you can replace your variable with your theta here. So I'm going to start with sine of x times cosine of 3 pi over 2. We are doing subtraction here, so I do want to use subtraction in my numerator. And I'm going to flip these around now. So sine of 3 pi over 2 and cosine of x. Any questions with the numerator piece of it? So essentially we just did the difference of signs identity in the numerator. And then we'll go ahead and do that difference of cosines in the denominator. So that's cosine of x, cosine of 3 pi over 2. Now we want to use a plus sign here, sine of x times cosine, sine, sorry. Ooh, yikes. Sine of 3 pi over 2. All right, let's simplify. So anywhere we got 3 pi over 2, we're going to go ahead and substitute in the value there. So what is cosine of 3 pi over 2? A 0. Awesome. So that's basically going to get rid of this first and the bottom piece even then, right? So if that's a 0, that's going to get rid of those two pieces. What is sine of 3 pi over 2? Because that's the only other one then that we've got to worry about. A -1. All right, so in the numerator, I'd have a minus -1 times cosine x. So that is going to turn into a +1 in the top. And in the bottom, I would get a -1 times sine of x. So that will stay a negative in the bottom. So cosine over sine is the same as our cotangent. So I'll replace that with our cotangent, and we have reached the end goal. So not too bad, as long as we can keep those formulas straight, right? That's going to be the tricky part. Any other questions with that? So the good news is those are the only 3 identities for the lesson. So once we get those copied down, it's just practicing from here on out. Okay. The degrees, I think you guys are going to do really well with the degrees. It's the radians I think we're going to struggle a little bit more with. But once we start getting some more practice with those radians, hopefully they'll become a little bit easier to deal with or to complete. Let's start with the degrees though first. We're looking at 75 degrees. 75 degrees is not on the unit circle right now, but we can add a couple values together or subtract to get the 75. Remember, try to keep them basic, smaller numbers. If you can work in quadrant 1 of the unit circle, you're going to be better off, right? So what values can you think of that we can add or subtract to get 75? 35 or 30 and 45 again, right? So let's go ahead and we would need to add those. All right, so now let's actually go ahead and use the sine formula. So I believe the sine formula starts out with sine of 45, right? Times cosine, it's one of each, I want to say. And are we using a plus sign or a minus sign with our sine formula here? It's going to be the same. Good. And then I'll just follow the actual formula this time around. So I'll flip the sine and cosine. Oh, that's technically not our final answer. Jumped the gun a little bit there. Because we can actually simplify from here then. We know what sine of 45 is, we know what cosine of 30 is, and the remaining pieces as well. So let's go ahead and substitute in those values. Let's start out with sine of 45. That's our square root 2 over 2. Yep. And cosine, there. Yep. So I'll go ahead and do that other one right away as well. Thanks. Cosine of 30. And sine of 30. It's got to be the 1/2 then. Okay. Remember I said there's only so many combinations on the unit circle for those x and y values. So you're going to see the same answer quite frequently, or a combination of that answer. So also simplifying it, you're going to get really fast at that as well. You're going to say, oh yeah, that's a square root of 6, that's a square root of 2. They're both over 4, so I can go ahead and write that final answer like so. All right, the next one is our radians, and this is where it gets a little bit more confusing. Can you guys list the radians for me? Right? List the radians for me that are located in quadrant 1. There's pi over 3, pi over 4, and pi over 6, correct? And then pi over 2. Okay. Yep, I almost forgot pi over 2. All right, these are going to be probably your most common radians that you look for. Now, we want to somehow get 5 pi over 12 by either adding or subtracting these. So because it's over 12, it helps to write them all with the same denominator. So let's go ahead and transform each of these so they have a denominator of 12. If I do that, pi over 3 is going to become 4 pi over 12. Pi over 4 becomes a 3 pi over 12. That'll be a 2 pi over 12 and a 6 pi over 12. Is everybody good with converting those so they have a denominator of 12? Okay. Now we just got to look for the combination that's going to either add or subtract to 5 pi over 12. I see it. Does anybody else see it? Which two values are going to give us 5 pi over 12? Yeah, these two right here in the middle. That corresponded to those two values right there, pi over 4 and pi over 6, right? So we're going to go ahead and add those two together. So I would always suggest, if you're running into a radians example like that, try converting your options to have the denominator that's given. So we had a denominator of 12 that was given. So we're going to convert those few options so they have a denominator of 12. It's easier to pick out the combination that way. All right, so this becomes tangent of pi over 4 plus pi over 6. And we're going to use that wonderful tangent formula. So we're going to start with the sum of sines identity in that numerator. So the sine is going to be, what is it? Sine of pi over 4 times cosine of pi over 6 plus, now I'm going off of memory here, so please double check my work and make sure I don't mess this up. Does that look good for the sum of sines in the numerator? Or do I need to tweak it? Stamp of approval. Awesome. So then we're going to go ahead and look at the sum of cosines in the denominator. So that's where I got to be careful here. See if I can remember this. Cosine of pi over 4. Cosine of pi over 6. What operation goes here? Yeah, awesome. So sine of pi over 4, sine of pi over 6. Okay, as I was typing this out, hopefully you guys were looking at the unit circle for what values we're going to substitute where. Let's start with sine of pi over 4. I'm going to need some extra space, so I'm going to come over here as long as I'm in blue. Hopefully we know that. Okay. Sine or cosine of pi over 6. So cosine of pi over 6, square root 3 over 2. Okay, good. Then cosine of pi over 4, that's our square root 2 over 2 again. What is sine of pi over 6? That's our 1/2. On to the denominator. We'll come back and simplify that in a moment, but on to the denominator. Cosine of pi over 4 is your square root 2 over 2. Cosine of pi over 6, we said that was your square root 3 over 2 minus square root 2 over 2. and sine of pi over 6 was the 1/2. All right, before we go too much further, any ideas what this is going to simplify to? All right, let's take a look here. In the numerator, I'm going to get a square root of 6 plus square root of 2 all over 4. And in the denominator, square root of 6 minus square root of 2 all over 4. The 4's will drop out, and you're left with the square root of 6 plus the square root of 2 over the square root of 6 minus the square root of 2. Yeah, so not so bad of a process, kind of an ugly answer, but the process along the way wasn't too bad. We just got to keep those formulas straight and not like switch up signs or anything along the way there. Tangent by far is the longest identity to work with the sum and difference here. All right, any questions with that one? I know, right? And the funny thing is not like it's like overly complicated, but the steps to get there, it's just so much writing, right? Like there's so many square roots you're dealing with, and there's so many, like you have to look at the unit circle so many times, and you're like, oh my gosh. And anytime there's a long process, then there's that chance of mistake, right? Even if it's just a copying, like transferring a number over mistake. So we just want to make sure we're paying close attention to writing the correct values down at the correct spots. And with the formulas being so close to each other, we want to make sure that we're not making a mistake there as well. Are we putting a plus sign where we need it? Are we using a minus sign when we are supposed to? Are we putting sine and cosine in the correct location in the formula? So lots of little things that we've got to just pay attention to. So it's all in the details with these problems. Okay, the good news is though, again, we're just practicing from here on out. So let's take a look at some more. These ones aren't too bad because we're working the problem in reverse. So can we actually find, write the expression of sine, cosine, or tangent of this specific angle? So the first thing we need to identify is which of the formulas we're using. Are we using sine, cosine, or tangent? So the first one here, Isaiah and Tommy said sine, all right, because it's got one of each, right? So with the sine formula, should I add or subtract the 42 and 17? Yeah, for sine, we copy that operation that we're using in the formula. So we are going to subtract here. What is 42 minus 17? 25. Awesome. We like these problems, right? All right, how about the next one? Are we using sine, cosine, or tangent? Sine again. All right. So it looks like we're working with pi over 3 and pi over 7. Do I want to add or subtract those two values? Subtract again because we just steal the sign that's in the middle. All right, this one we have a little bit extra work to do because we can't technically subtract until we have a common denominator. What is the common denominator between 3 and 7? $21. So we're going to rewrite this as 7 pi over 21 minus 3 pi over 21. What is 7 pi over 21 minus 3 pi over 21? 4 pi over 21. Good. That's definitely not on the unit circle. Well, like a specific point, I should say. Questions with the first two? All right, this is just continuing on, so we need to condense this. Is this sine, cosine, or tangent? This one's cosine. Now, does it fit the formula exactly, or do we need to switch the two pieces? This one fits exactly, right? Because cosine comes first, sine comes second. So we do not need to flip it to match that formula. So if we don't need to flip it, then we're just going to do cosine. And should I add or subtract the 7y and 3y? Yep, we do the opposite of what's in here for cosine. So we are going to add 7y plus 3y is my 10y. Let's hope the homework assignment consists of all these type of questions, right? If we were only so lucky. All right, last one for today. We need to prove the identity here. All right, so to prove the identity, let's just perform the difference of signs and then the sum of signs, and then we'll add those together, and hopefully something is going to cancel along the way to give us this remaining piece over here. Let's start with sine of x minus y. If I were to substitute these into the formula for the difference of signs, what would we get in return? So if we were to apply the difference of signs in the first piece, what would we get? Okay, everybody good with the red formula there? They match up. Tommy and Isaias had it there the same, so that's always good. All right, let's see what's going to happen with the sum for sine here. What do we get when we do the sum of signs? Okay, I copied what Isaias had down there. Everybody agree with Isaias' response there in blue for the sum of signs? All right, let's look for like terms. Are there any like terms that we can combine? Yep, so those are identical. So technically you have a 1 in front of each of those. Yep, so that becomes a 2 sine x cosine y. And then the remaining pieces that are not highlighted are also like terms. Cosine x sine y. They are opposite of each other. You have a -1 plus 1, so those are going to cancel. Those go to 0. So we're left with just 2 sine x cosine y, which is what we were trying to prove. Yay! Nice short one for a change. A nice one to lead us into winter break too. All right, so hopefully you guys feel pretty good about the sum and difference of sine, cosine, and tangent. Just pay attention to detail, take it slowly, make sure you don't make any mistakes as you're substituting values in to the formulas and then simplifying. If you just take it slowly, you should be pretty good with the 5.03 lesson. All right, that's all I have though for you guys. So before I forget, I just want to say happy holidays, Merry Christmas, Happy Hanukkah, Feliz Navidad, and Happy New Year as well. So I won't actually see you guys again until 2018. Isn't that crazy to think that the next time I'll see you will be in 2018? I know. Ah. All right, I'll let you guys go though. Have a great winter break, and I will see you all in the new year. Bye, everyone.